Thank you. So the short answer to your question is that I don't think God plays dice, but he might be playing chess, is the short answer. But I hope it will become clear during this presentation. What I'm going to try to squeeze in less than an hour is actually almost 20 years of work. That's something I've been working on for really a long time. And I'm going to present it to you in the order in which things happened, meaning that it's first game theory, that then extended into quantum theory in quite a very natural way. So what I'm going to do on this journey to try to convince you that Einstein might actually have been right is start with game theory and introduce you to an alternative way of doing game theory, to Nash equilibrium. Who knows John Nash? Many of you, right? And so I call it non-Nashian, but just like we say non-Euclidean geometry, right? It's not against John Nash, on the contrary, it's a tribute to him. And then I'll go into quantum physics. All right, so let's start with the game theory 101. So I'll start with the mainstream, right? The first, the one that everybody accepts. So what is game theory? It is a way of modeling the interaction between agents that we consider to be logical and rational. So in that talk, I will take Peter and Mary. Sometimes I call them Alice and Bob, but Peter and Mary seem to have been introduced by Jean-Pierre Dupuis at Stanford that I worked a little bit with, so I kept this habit. And in that case, the prisoner's dilemma says that these two persons can either cooperate with each other or defect and not cooperate with each other. Of course, that in itself is not enough to specify a game. In order to specify a game, I can do it in this way. This is one of the main two ways of modeling a game, and I'll show the other one a bit later. This is called a game in normal form. Why? Because we have a matrix. We have here Mary's choice, defect or cooperate, and then we have Peter's choice, defect or cooperate. Think of them as being in separate rooms. They each have to make a choice. Of course, they can think about what the other person is likely to do. And what happens is that once they make a choice, for example, Mary's choice could be to cooperate and Peter's choice would be to defect, they land here. And the two numbers we have here is on the left what goes to Mary, and on the right what goes to Peter. You can think of these as Swiss francs, but it's actually called a utility. It doesn't have to be exactly money, but basically we assume they want to have as high as possible in terms of what we call rational preferences, right? So this is called a game in normal form, right? So far so good. So now there's a whole theory that was developed by John Nash on how we actually solve these games or how we explain what people will or should do. And the idea is this. I'm going to take Mary's place and think, what should I do? And I'm going to do it in two steps. First, I assume, okay, imagine that Peter, in the other room, is choosing to defect. So I'm going to lock on that and then optimize. And then I'm going to do the same thing with cooperate. Well, when I do that, I should look at the left number, right? Because I'm Mary, so I should be interested in what I'm getting, which is on the left. And then I compare only vertically. Very, very important, vertically. Because if on the other room, Peter is actually defecting, then depending on what choice I make, I'm going to get 1 if I defect and 0 if I cooperate, holding Peter's choice as fixed. So of course I should defect, right? If Peter defects, I should defect. But if Peter cooperates, what should I do? Well, here I get 3 instead of 2, I should also defect. So it's a coincidence that in that game, in both cases, we should defect. It's not always the case. But when it happens that no matter what the other does, if I fix it, I should always do the same. That's called the dominant strategy. That's what we call it. So in other words, defect is the best response both to the opponent defecting and to the opponent cooperating. So it seems to be logical, and that's what the Nash equilibrium says, what John Nash would have said, is that since whatever the opponent does, my best response is always to defect, then I should just defect, right? Now you notice the game is symmetric, right? It's exactly the same thing for both players. It's totally symmetric, so I can make exactly the same argument for Peter. So Peter should also defect. So what's the result of that? Mary defects, Peter defects, and we have a Nash equilibrium. And again, how do I define the Nash equilibrium? Knowing this, none of them have an interest to change what they are doing or to deviate. Why? Mary could change to here, she would get less. Peter would change to here, he would get less. This is an equilibrium. They both stay here and they defect. But you probably see the problem, right? Because they are here and they are missing an opportunity where both of them would have gotten something better. That's called the Pareto improvements. It's a bit sad, right? That we are stuck in here in a Nash equilibrium. That's why it's called the prisoner's dilemma. And we would have gotten something better if we had both cooperated. This is John Nash, by the way. All right. So is there any other way to think about this? And here we enter the universe of non-Nashian game theory, just like non-Euclidean geometry. It's a completely different way of reasoning. And the earliest account that I found of this kind of reasoning actually dates back to 1983. And it's due to Douglas Hofstadter, who read Gödel-Escher-Bach, the book, some of you, Pulitzer Prize, so very, very talented. And he had a brilliant idea back in 1983. So this is Douglas Hofstadter. And Douglas Hofstadter thought in the following way. The game is symmetric, so the two players should anyway make the same choice, right? Even in the Nash equilibrium, they make the same choice. They both defect. So basically, if the game is symmetric, we can take as granted that they will make the same choice anyway. They will never be in a situation like one defects, the other cooperates, or vice versa. So that means that we can kind of eliminate from the very beginning these two. It's kind of a higher level of thinking that we already know they will pick the same. And then we optimize like this on the diagonal, and every one of them prefers to pick two rather than one, right? And this means that the equilibrium, that's called super rationality, in that case, defined for symmetric games, gives you 2, 2. Now we are Pareto optimal. We cannot improve that, right? So this was the contribution made in 1983. We will get into the details of this idea because it might be surprising or counterintuitive at first, right? If you are trained to think as Nash equilibria, has to do with the notion of free choice. What's very important here is to understand that these two here, when you think I cooperate and she cooperates, if I had defected, the other would have defected as well. This is a conditional tense that's called a counterfactual dependency, right? So it's the subjunctive mood right there. And I'm giving you an example to make the difference between causal and counterfactual, in the sense that here is the indicative mood. Uri Schwitz and Unterwald signed a pact in 1291 because the Habsburg tried to invade their region. That's the indicative mood. In the counterfactual subjunctive mood, we say if Uri Schwitz and Unterwald had not signed the pact, then Switzerland would not exist as it is today. It's counterfactual because I'm considering some hypothetical parallel worlds in my imagination that could have happened. And this can really be recognized with the subjunctive mood. And this is what I said when I said we both cooperate, because if I had not cooperated, the opponent would also not have cooperated. This is why the diagonal. And now I would like to show you this, because this dates back to 1930, I think 1935, around this, the famous Einstein-Podolsky-Rosen paradox was a paper published back then. And I noticed here, because I was curious, this here is a subjunctive tense. And I think it's not a coincidence. So it's somehow, this is done right? When we are looking at alternate experiments we could have done, then this should be spoken in English and in terms of the subjunctive conditional. And they also have something very interesting, because the word change sometimes, maybe I will have a bit time to explain why one should be very careful using the word change when considering hypothetical different choices. No real change can take place in the second system in consequence. Why? Because it's not in the future, right? So you can only impact things that are in your future. All right, but this is just, all I wanted to show to you is the subjunctive conditional in there. So you see the difference between Nash and Hofstadter, so these two approaches, is really in the structure in which we compare the numbers, right? In Nash, we are really locked horizontally or vertically, and in Hofstadter's case, we are looking through the diagonal. And this is why the concept of a Nash equilibrium, or the Nashian reasoning, is tied to the concept of free choice, in the sense that I can freely change my strategy, free in the sense of locking the opponent's strategy, while for Douglas-Hofstadter, it's not free in that sense. It's just a weakened version, right? But I'll come back to that. So far, so good? The difference between the two? All right. So this is why we have these two different results, because in that case, we're comparing like this, and in this case, we're comparing diagonally. All right. That was the Game Theory 101, 4 games in normal form, people in separate rooms. Now I'm going to move on to something else that usually is what I start with when I explain this line of research to other people. It's called the Newcomb's paradox. And in a way, the Newcomb's paradox is the Schrödinger's cat of free choice. And this is actually, it was already thought in this way back then when I started working on this, which was already giving a hint that something is going on with quantum. So let me just directly tell you. Who knows the Newcomb's problem or Newcomb's paradox? Some of you. All right. So this paradox, just like Schrödinger's cat, is basically bringing to our scale the concept of quantum superposition. In the Newcomb problem, we bring to our scale the concept of predicting what people do when they have free choice. So there is this apparent contradiction, right? If somebody predicts what I'm about to do and already knows what I'm about to do, am I still free to do what I want if it's already been predicted, right? So that's kind of a tension here, right? Which side is the stronger, right? Between being free of choosing what I want and being predicted in my choice. So here's the paradox. There are 2 boxes in front of you. In one box, there is either $1 million or 0, but you don't know because the box is closed and you cannot see through it. But in the other box, it's open and you see that there is $1,000, right? So either this or this, the 2 boxes. And you are given the choice between either taking one box, this one, and you get whatever is inside, or the 2 boxes, and you get everything that is inside, right? So either just this one, or the 2 of them. As you might imagine, there is a catch, because otherwise it would be too easy, right? So here's the catch. Somebody in the past, there's many ways of defining this. Could be one of your best friends who knows you very well. Could be some supercomputer. There is also a professor, Rich Schifrin, University of Indiana, who likes to say, this person is yourself, but then you took some medication that made you forget, so it's actually you. Which is also, it triggers your right, you have to think a lot through this problem. So if whoever this is decided or predicted that we would take only one box, then they will have put $1 million in the box. This is a given. There is a direct causal link between the prediction of one box, and putting $1 million in there. And if the prediction was made that you would take 2 boxes, then this person will have put nothing in there. That's also a given. So now, do you take 1 or 2 boxes? Who picks 1 box? Who picks 2 boxes? Right. So you see, it's a bit divided. If I had given this talk in an institute of theoretical physics or in an institute of economics, everybody would have raised these two boxes, the hand for 2 boxes. But I will explain now why. But the fact that it's divided is general. If you ask people in general, it will be more divided than for physicists and for economists. So here's the reasoning of those who pick 2 boxes. Let's call X what is in the closed box. I assume that whatever I do is independent of X, right? Because it's in the past, cannot change the past. So let's call it X. I have the choice between X plus 1,000 and X. So obviously I take X plus 1,000, right? And that actually gives me 1,000, because then it's going to be empty probably. But this is the idea, right? And then the other reasoning is that I should pick 1 million. Because I'm comparing 1 million to 1,000. And here I'm thinking, it's different, I'm thinking that if I had picked 2 boxes, there would have been nothing in there, right? It's a counterfactual consequence. So it seems that both reasonings are correct, right? So there must be something, that's why it's called a paradox. But actually, if you look deeper into it, as I will explain, the difference is pretty much the same difference as earlier between Nash and Hofstadter, as I will explain now. Here's why. Because when you make a decision, you're always comparing what you do with what you could have done. What does it mean, what you could have done? It's a parallel world in which your decision is different. So above here, that's our world, where we are right now. And here I'm thinking about the two-boxer approach, those who pick two boxes. The person is going to take two boxes. The prediction is correct. Alice in the past predicted that Bob would take two boxes. But then Bob, to make his decision, is considering the alternative. What if I had taken one box, right? But for the two boxers, that I put two or one box, this is independent, right? So it doesn't change. So no matter what I take, it's already going to have been predicted that I take two boxes, right? I would just make the prediction wrong if I took one box instead. So I'm comparing $1,000 to 0, and thus I take two boxes, right? So this is rational reasoning. So note the fixity of the past, right? So this is the free choice in that sense, that whatever I do is independent of the past. Now, the ones who pick one box, this is then the same drawing with the actual world in there. Bob takes one box, and it was predicted that he would take one box. He has free will, but not in the first sense. It's a weakened version of free will in the sense that he could have taken two boxes. So there is an alternate world in which two boxes are taken. But you see that now there is a counterfactual dependency. That's this subjunctive mood, right? If Bob had taken two boxes, Alice would have predicted that Bob would have taken two boxes, right? Because from the perspective of our world, this is an alternate world. This is called perfect prediction. It means I could have made another choice, but if I had made another choice, the prediction would also have been correct, right? So you're basically looking at all these parallel worlds where you have this counterfactual dependency between the two, right? It's not causal. You cannot have any causal effect to the past. You're just looking at counterfactual dependencies. So now you're comparing 1,000,000 to 1,000, so you take 1,000,000,000. All right. Just to give you, because that's the Newcomb problem, I'm going to do the same thing for the game that I've shown earlier. When we compare with the horizontal line, Bob defects and Alice defects, so they both get 1. And now the counterfactual, if Bob had cooperated, Alice would still have defected. This is because you assume it's independent. That's the Nash equilibrium. So you get 1/0, and thus you defect because that's your best reference to Alice defecting. Now, if I analyze the super-rational equilibrium, Bob cooperates and Alice cooperates. We are here, but what does it mean that we are comparing along the diagonal? It means that if Bob had defected, Alice would also have defected. That's a counterfactual dependency, right? So that's, again, the perfect prediction. So you see now we are comparing 2 to 1. Both of them are rational. So you see what difference is there between the two? It's all in the assumption. In this case, we are assuming that we have free will in the sense that the past is completely independent from what I'm doing. I cannot change it with my decision, so it's fixed. Then that's the Nash equilibrium. And the non-Nashian reasoning happens when you believe that there is a counterfactual dependency and that if you had made your decision in a different way, it would have been predicted, something else would have happened. So far, so good? Is everybody following? Yes? Okay. So just a first pointer to literature. That was a couple of years ago now. In this paper, I generalized the reasoning of Douglas Hofstadter, which is only for symmetric games, for all games, even when they are not symmetric, right? So this is a generalization called the perfectly transparent equilibrium. That's non-Nashian, and it's a generalization because in the case of symmetric games, then you land back on Douglas Hofstadter's equilibrium, right? So it works on non-symmetric games. The only assumption is that there are no ties in the payoff. Okay. So we covered 1/2 of game theory, right? The games in normal form. There is another kind of games, a bit more like chess, where you play in turn, right? Civilization. So if you play in turn, it looks more like a tree rather than a matrix, just a different kind of game, but you still have this idea of having payoffs in there, right? So here I put Peter first on the left, gets 2, Mary gets 0, if that's the outcome of the game. But in order to reach the outcome, there is a series of decisions. It's like a bit like a decision tree. Then it means that Peter goes to the right, Mary is here, and Peter here, and we reach that outcome. Peter gets 2, and Mary gets 0. And of course, we need to play this. For chess, of course, the size of this would be absolutely gigantic. All right, so that's the game. I'm not going to be showing the resolution on that one because I need to keep it simple to fit it into the allocated time. So instead, I'm going to focus on that game, but you agree it's also a tree, right? It's just a bit simpler, right? It starts here, Peter can go here or here, Mary can go here or here. If she goes here, Peter can go here or here, and so on. That's called the centipede game, this kind of game. Or the take or leave game in that sense. It's basically the idea that there is a pot on the table, a pot of money, and somebody keeps adding dollars, and you can, in turn, take it or leave it, right? So if you take it, you take everything, and otherwise the other person gets it, right? That's kind of the general explanation. All right. So how do we solve that the Nash way, assuming that there is free choice? Well, you might have heard of the backward induction. When you play chess in that way, you start at the end, and then go backwards, you backtrack everything given your anticipation of the past. So we are going to start right there. So Mary has the choice, she's on the right here, 3 or 4, she obviously picks 4, right? And she doesn't care about the past because again, that's totally independent, right? Then Peter knows about that. He's simulating maybe Alice, he knows that in the future, if he goes there, Alice would pick that, and he would get 2, so he would better stop here and instead take 3, right? And that is not going to happen, right? Then, knowing that, Alice here knows that if she was going there, the resolution of that sub-game would give her 1. She's better off stopping here and getting 2. But then Peter knows here that if he would make this decision, he would get 0, knowing the resolution of that sub-game. So we'll end here. Peter, at the very beginning, takes the money from the pot and gets 1. This is the Nash equilibrium. It's also called, in that case, a sub-game perfect equilibrium, because you resolve the game in every sub-game and work your way recursively upwards in the tree. Something very important here, because that will be related a bit to quantum theory, is that in this Nash equilibrium, these decisions are also defined as hypothetical futures, even though they do not happen, because the actual timeline is that Peter stops and we stop here. All of these decisions, they are in their minds, right? But they are still defined, even though they do not happen. I'm just noting that for later. So far, so good. Who understands the Nash equilibrium? Okay, so that's the Nash resolution. You see, it's not very satisfying, right? Because Peter gets 1, but they could have gotten something better here, right? Both of them would have something better. So it's not always Pareto optimal. Then I'm going to give you the non-Nashian version of this to show you the thinking behind this. The seed of that was actually given in the 90s and in the early 2000s by Jean-Pierre Dupuis, who is a professor at Stanford, and with whom I worked a little bit at the beginning, taking on his ideas. And what he had as an idea, that's the non-Nashian reasoning, is that we should think of the game as happening in a timeline. So you have to play the game and follow a path. The path has to be consistent, so there is some causation in the dynamics of the game. But at the same time, if we assume perfect prediction, meaning that the players anticipate what the resolution of the game is going to be, and even if the resolution had been different, they would also have anticipated it, that is non-Nashian thinking, it turns the whole thing into a fixed point equation. You have to find the outcome of the game that resists its being known in advance. So you know the outcome of the game, you know in advance this is going to happen, and in spite of knowing that it's going to happen, you play towards making it happen. Or even more precisely, the fact that you know it's going to happen causes you to make it happen, also known as a self-fulfilling prophecy. So this is a fixed point equation, and the resolution is all about finding this fixed point that is immune to being known in advance. So in other words, we want to avoid the grandfather's paradox, if you like, time travel movies. So the reasoning is twofold. There are these 2 principles that I'm going to apply on the game. The first principle says that if I anticipate an outcome I don't like because if I would deviate, I would get something better. That's called preemption. The second principle is that if everything is better here than there, then I'm going to go for the parts that I like, right? But let's put them in practice, much easier. Here's the idea. It's a reductio ad absurdum. I'm looking at a fixed point equation, so I'm just going to eliminate what is not the fixed points in order to pinpoint the fixed point. In that case, it turns out that we don't go right to left, but left to right somehow. And the idea is that I'm asking the question, can this be the solution? Can this be the outcome of the game, and everybody knows it in advance? Surely not, right? Because Peter here, if he knew that this were the solution of the game, he would get 0. This is inconsistent because he's rational. He would obviously pick 1. So what happened here is a reductio ad absurdum. I'm showing that it's absurd that this could be the solution of the game because Peter would never willingly go there, knowing in advance that he would get 0 if we can get just 1. So we eliminate that. That cannot be a fixed point. Now they integrate it in their thinking. Now you notice that here, 3, 2, 5, the only that are left, they are all larger than 1. So Peter goes there, knowing that 0, 2 would be inconsistent, right? There is a counterfactual dependency. If Alice would go there, Peter would have known and gone there. It's a grandfather's paradox, right? You travel back to the past and prevent your parents from meeting. So, yeah, I love Back to the Future. All right, so then Alice goes there because of that grandfather's paradox avoidance. Then we do the same thing here. Could this be the solution? No, because if Peter knew that in advance, he would go there. That's incompatible, so reductio ad absurdum. That's not a fixed point. And now 5 is greater than 3. So we go there. This is it's called the perfect prediction equilibrium for this kind of game. That's the non-Nash resolution. All right, for whom does that make sense? All right, it's again a fixed point equation, and I'm just eliminating the outcomes one by one. We have 2 theorems that actually dates back to 2004, but can you believe it? It took 14 years to get that published because that's away from the mainstream. But we have 2 theorems. Is that so the perfectly transparent equilibrium is just the general name. It's always at most unique. You cannot have multiple of them. There's at most 1 fixed point. And the second theorem is that it's always Pareto optimal, meaning you will not be stuck in situations like the prisoner's dilemma where you would have another outcome giving more. That cannot happen. It's always optimal. So it's very desirable from an economic perspective. All right, the other paper for extensive form, it's right there. That's also published. You can read it. It actually was published before the normal form version, but you can also take a look at it. See, it took 14 years from 2004. The only thing we changed there is not the algorithm. This was unchanged for 14 years. It's the pedagogy, the way we explained it that we changed. All right, and now I'm getting to quantum. Quantum theory, let me give a 101. Don't worry, you don't need to have the Schrödinger equation or anything, because it's a very particular high-level view. First, there's a lot of intuitive things in quantum theory. For example, one of the most disturbing things that happens is that you throw electrons, which are particles of matter, you throw them through 2 holes like this. So you would expect to see a first trace here and a second trace here for the 2 holes, right? No, that's not what you see. You see actually something like interference, the sort of things you see in your living room when the light goes through the curtains. That's very surprising, super surprising. So it seems that there is something new in there, and that actually turns the whole field of physics upside down in the 20th century, right? So then there was a huge discussion going in all directions, leading us to a point that we have a theory that works. It's very good at explaining everything. We just do the math and do it. But we have to deal with superposition and entanglements. The measurement changes the system. When you observe something, it changes the system. Randomness that we have to live with. Spooky action at a distance, that the term coined by Einstein back then in the EPR experiment, Einstein-Podolsky-Rosen. And Richard Feynman was even quoted to say that, I think I can safely say that nobody understands quantum mechanics, right? He was very good in his lectures. And to make it worse, we even have impossibility theorems that deny us some principles that before were assumed as obvious, such as when you look at something, it's just there, you look at it and you see it, realism. And locality, which means that nothing can propagate faster than light, right? It's spooky action at a distance. And this is gone. We don't have that anymore. We have to get rid of that somehow. So that's absolutely terrible, and Einstein actually was fighting against this. Like, there has to be a better way, right? We were just missing something. So I'm going to try to defend Einstein's view and to show you that there is actually a better way. And I'm going, of course, to give you arguments, because I'm just not going to wave in the air. So I hope that these arguments will make sense. So who heard of a quantum measurement? Who heard of collapse of the wave function? That's the terrible thing that happens when you look at something, bam, just collapses. So here it's kind of a superposition of multiple places, something called as the wave function. It's some sort of probability amplitude, except that it has colors there, known as the phase. And then, bam, you look at it, it's there, and that's collapse. That's one of the ways, not everybody sees it that way, but that's one of the ways of seeing it, is that nature makes a choice about some position, and that's it, and now you see it, and it's there. And it seems to be random. We cannot do anything else than say, okay, with some probability, like this is the density function, the square of that actually, but this is the density function, and then it gives you a probability, and you toss a coin and get that, right? And that's the thing that disturbed Einstein, and that disturbs me too. Now, how can we abstract away? Because of course you can read the whole quantum physics book and look at the equations of the photons, the electrons, all the terminology, but there is a field known as quantum foundations where we kind of abstracted away. One of the abstractions is that we think in terms of qubits, so just 0 and 1, simplifies a lot compared to an infinity of position. And then we just look at it from outside. I don't know you, but I've never seen a wave function. I've never seen a quantum state. What I've seen, however, is some knobs that I can turn to make a measurement, and then I can read the result somewhere. That I have seen. These are the classical bits. The quantum is just underneath. We don't see it. We can have a theory that explains it. But the only thing we observe, and based on which we derive our theories, is based on this. So the idea when you prepare an experiment is that you prepare a system, you spit out some electrons or photons or protons or whatever. You turn some knobs to select a setting. For example, you measure a spin on the X or Z axis, so make a choice. Then you see a result. Maybe it's up, maybe it's down. I put 1 and -1 in there, right? And then you record it to some medium, maybe in an Excel spreadsheet or in some file or on some textbook, but you write it down somewhere, classical bits. All right, so this is the abstraction that we're going to have. So there is a setting, there is a result. Now, I just wanted to show you the Richard Feynman version of this, because he actually gave plenty of wonderful lectures, and this is how he draws this, right? So you push a button there, that's your knob, and you see a light bulb that either switches on or doesn't. So that's just to show you the level of abstraction that we have here. You make a choice on what to look at, setting, turn a knob or push buttons, and then you see the result on some screen or a light bulb that switches on or off. Now, I'm just giving a bit of food for thoughts for the physicist. Who is a physicist? We have some. So I need to basically be a bit more formal and make sure that you understand what I'm talking about. So here I'm referring to a paper published right here at ETH, the Institute of Theoretical Physics. So the idea is that if you look at a local experiment, what you have is you make a measurement. So this is my setting here, and this is my outcome there. But you need to feed a quantum state in there. That's what I don't see, but it's the input. And then you make a measurement, turn the knob with a specific setting that you pick, get a result, and then you spit out something to the outside world. I'm giving you the fancy words. Don't worry, everybody else. My input and output quantum state is a density matrix in the linear space corresponding to the Hilbert space. My measurement setting is just a classical value, and my measurement outcome is a classical value. And what is in the middle, mapping all of that to this, is called a CPTP map. Completely positive, trace-preserving map. I'm not going to explain what that is, but I know that the physicist gets what I mean, right? And in this paper, in the original paper that is actually here, it's not done in that way, but in this paper, it's reformulated by feeding the classical as part of the input like this and having the CPTP map work on everything, right? I think it's a very nice way of putting it, right? But basically, this is what we have. We have the local lab. Now let's look at two labs, Alice's lab and Bob's lab. So now I'm going to have a lab right here and right there, and I can connect them. For example, I can see that Alice is before Bob, and the output state of Alice goes to Bob, right? And again, these are my two knobs. These are my two outcomes, right? I could also connect them in that way, right? Prepare some entangled particles, and I ship one over to Alice and the other to Bob. They're entangled. And then they just do their measurements very far away from each other so that they can't communicate. So this is what we would get. Again, I have my two settings and my two outputs there. Now, what we are interested in, because that's the only thing I can actually observe, is the statistical distribution of my outcomes, x1 and x2, conditions on specific choices of settings, right? So are there students of mine, information retrieval, who saw, yeah, I put it the right way, right? So really explicitly the random variable, the classical variable, and so on. You can also write it this way, which might be a bit more compact. So it's really the probability of getting these two values conditioned on the fact that we get these two values. Now, what is that actually? If I do it 1,000,000 times, I'm going to log that to some book, right? I keep records. Then I aggregate, and what I get is a table like this. If you're familiar with Bayesian networks, that actually shouldn't surprise you. But basically, I have the value of this, the conditional probability of the two outcomes conditioned on the settings. And here, maybe I can collect the statistics of that, the frequency. It only sums up to 1 within each choice of the settings, right? So this sums up to 1, this, and this separately. This is the case where we have an entangled particle, and I think we measure on X or Z on the left, and on the right it's some more complex thing, but basically it gives us these probabilities right there, this distribution right here. Now, you could also do a different experiment and just don't use quantum state and just toss a coin, right? And then you just get a quarter probability, 0.25 everywhere, right? So these are just two experiments. You can just do whatever experiment you want. Then you log the values in there, the probabilities. Now, there is a criterion. That's the Bell inequality. The Bell inequalities, actually, there's plenty of them. It's a way to detect quantumness. It's a way to say, okay, here that cannot have been something non-quantum, cannot be something classical. So I just threw the formula at you like that, which applies under two assumptions. Free choice, same that I explained earlier. Your choice of settings is independent, or the past is not, sorry, let me explain it precisely. Your choice of setting can only be correlated to stuff in the future, not the past and the present. And local realism is the idea that nothing propagates faster than light, and measurement outcomes are pre-existing. The two are tied, actually. In the original paper, there is an argument that this kind of implies that with free choice. Anyway, but I don't want you to be scared that formula, so I have a better way of explaining that. So your detector of quantumness just consists in adding up the purple cells in there, and you look, is that greater than 1? If it's greater than 1, then that could have been classical. If it's smaller than 1, then that's not possible that it's classical. There has to be a quantum thing in there. And we know that this happens in nature, that it's smaller than 1. We know that nature breaks the Bell inequalities, and this is what Alain Aspect proved earlier. So now, if we do that with the classical setting, I find something greater than 1. Great. Nothing to write home about. Now, if somebody comes to me and pretends that they run this experiment just with coins and dice, and they give me that table, I'm going to say, no, there's no way you could have done that with coins and dice, because if I sum up all of these numbers in the purple cells, I get 0.59. So there has to be something that is non-classical, right? So that's the idea. But you see that everything there is just based on my probabilities or statistical distribution in my outputs. So now, how do I move on to maybe an alternate way based on game theory to potentially explain that sort of quantumness? Well, I could draw what's called the causal diagram here. So I'm giving that, again, as food for those for whom that makes sense. So A1, the choice of setting causes the outcome because it's in the past. And you will also see a lambda that kind of have been some state of the past that influences both outcomes, right? What's important is that A1 and A2, they are called exogenous. They are not influenced by anything. They are just freely chosen. I'm going to remove lambda because I'm focusing on this for non-Nash approach. The first thing I'm going to do is duplicate the choices. Why do I do that? Because I have information. here, that's the choice by the universe of the outcome, knowing that the knob was on 0, and here it's the choice knowing that it was on 1. So I basically pretend, okay, these are two different choices. So this is like a game. That's called a space-time game, actually. And you see, what are the possibilities here? This is a possible outcome. This. I'm just listing all the possibilities here. There are basically 16 possibilities. It turns out that I can represent this in that way as a game. See, it's game theory again with the settings and the outcomes. The payoffs here are three parameters of the model. I can put whatever I want, and it's future work to actually know what to put in there. Actions, for example, nature minimizes action. And then you will find that in the paper, the space-time game and so on, just giving you the reference. If you solve it in the Nash way, you will find this equilibrium. But look, it has locality all over the place, right? Because this is when I say that I cannot distinguish between this and this with the dashed line, that's because I'm far away from it, so I cannot know the result here. It has realism all over the place, because this here is the results of the measurements that are predefined, right? And then you go through there and read the results. But it's not Nash, because if I deviate, I will always find something less. So 10 is better than 9, so the deviation doesn't give me anything, right? And all the deviations that I try, I always find something less good. That's why it's a Nash equilibrium, right? Even that doesn't even impact anything. So this is why we have a Nash equilibrium. But you see, we have here free choice and local realism. So in the paper, we established a link with the Bell inequalities that it's not possible to break them. It's not possible to explain quantumness with Nash equilibria. You will find more in this paper that I co-authored with one of my assistants, Michał Banczyk, who worked with me during the pandemic. We did a lot of stuff on Zoom. All right, and now the non-Nashian resolution, just the animation. The idea is that you do the same elimination that I told you, and you eliminate what is not possible. Here, you eliminate this one because you would always get something better here. And you just work your way like this, eliminating, and you see there's an elapse of time here, right? That leads all the way with the forward induction to some results. And here we have local realism, but we don't have Nashian free choice. We have the reduced free choice, as I explained earlier. And so I like this quote of Sir Arthur Conan Doyle in Sherlock Holmes, which basically says, "How often have I said to you that when you have eliminated the impossible, all the outcomes that are not fixed points, whatever remains, however improbable, must be the truth, the actual world in which we are, and the result of the experiments that we carry out." The algorithm for resolving the game is in a separate paper that you will find here. It's also all explained with the algorithms, formulas, and so on, how to solve in a non-Nashian way. There could be other non-Nashian solution concepts, right? It's just one of them. And in order to finish this talk, I would like to give you an intuition on this idea of causation, counterfactuals, correlations, with the idea that you can think of this whole thing as space-time, but you add a dimension to parallel worlds. Like, who knows the Sliders series? It's an awesome series from the 90s, 2000s. They open a vortex and travel to parallel worlds. And this could be seen as an extra set of dimensions here, which are going to the parallel worlds. And so on the very, very high level, in a way, time is linked to relativity theory that revolutionized causality, space to information theory that revolutionized correlations. Why? Because the correlations are about something that is logged in a textbook. It's stored on a hard drive. So this is on space. And HAP, that's what I call the other dimension because of happenstance, is about quantum physics that revolutionized counterfactuals. It's all about counterfactuals, right? I measure up, Alice measures down. If I had measured down, she would have measured up. That's a counterfactual dependency. So this is the summary here. Interestingly, these three causal, counterfactual, statistical, I believe they should be different. That's what I strongly argue, but a lot of people confuse them. The easy one is causal correlations. You've seen these chocolates versus Nobel Prize thing, so everybody knows correlation is not causation, right? But the other two is not so obvious, right? Because we have a lot of people who kind of define causation, information theoretically, with counterfactuals, right? Something causes something else if when you change the first, it changes the second, right? That's the counterfactual. And the third one, counterfactuals and dependencies. I had a student, Emilien Piou, who worked with me. It's about the difference between conditional probabilities, indicative mood, and counterfactual probabilities of subjunctive conditionals. That's what this means here. And in a way, one easy way of summing that up that I heard sometimes in the community, it's not by me, is the idea that you try to work with probabilities in the quantum world, but there is no omega space. You cannot patch together all of the mini omega spaces into a single one, so something's odd. And I think the reason is that these are not conditional probabilities, these are probabilities of subjunctive counterfactuals. So the idea, what motivates me in there is quotes like this by Bell, because a lot of people interpret the Bell inequalities as showing that Einstein was wrong. You cannot have hidden variables or local realism. But he said, Langmaid-Wiedebreu, who invented a theory that is non-local, continue to inspire those who suspect that what is proved by impossibility proofs is lack of imagination. That's a very inspiring quote. But in short, I mean, the argument we have is very simple. There are two assumptions for Bell inequalities, free choice and local realism, right? But since there are two assumptions, most people drop local realism, no hidden variables. We do the opposite. We think there is local realism. It's all predefined in a way that we can predict, but it could have been different if we made different choices. So we do have a weakened form of free choice. We just decide to drop the other assumption to the Bell inequalities rather than the first one, right? So I would like to thank all of the students who have been working with me in various projects. So this was really instrumental to all of these results, right? So if you're interested, you can read the papers, or we can maybe have some questions now to take it further. So thank you very much for following.
Thank you very much, Ghislain, for this very interesting talk. So we have time for only a few questions, but I hope you're still around outside if
yes.
People have some more questions.
Absolutely.
So let's take, like, I think 3 questions, depending on how complicated they are and how long they take to answer.
So at the end, you mentioned that you are able to retain realism, and by assuming this counterfactuals, that if it were different, it could have been different. Can you interpret this similar to the many worlds interpretation of quantum mechanics?
Yes, I can explain that in context. Actually, I dropped another 100 slides that talk about that, but that I could not put in there in the interest of time. The way that I think about how it fits with the many worlds interpretation is that when you have a game like that, these are all the many worlds. They all appear here. But the many world interpretation has some symmetry between the worlds. These are all possibilities, and we just happen to be in one of the worlds, seems random, and there are all the other worlds that could have been. What this adds, this model, it's a model because, again, you need to instantiate the parameters, so it's only a model. The idea is that it builds on top of the many worlds by pinpointing one of these worlds as being the world in which we are. So this is asymmetric because there is really one of these that is the actual world. But in essence, it works on top of the many worlds, but it eliminates all of the worlds that are inconsistent in this setting, and that only leaves one, at most one.
So it would be closer to the Feynman's path integral interpretation. Where
Yes, exactly. That's exactly the idea. That's exactly what it is, and there is a direct link with this idea. Yeah.
Okay, thank you.
Any more questions?
Sorry, maybe for having missed something, but at the end I didn't understand. Are we free to make a choice or not? Because if it is because we were going to choose that, it was given this realism, or however you want to call it, because I think there was a little bit mix in the concepts. This also implies our choice or not? This was not clear for me. Thank you very much.
So free choice is something that we are kind of emotionally attached to, right? So we kind of want to hold on to it. What I'm interested in is the mathematical definitions of free choice. The mathematical definition that you commonly find of free choice in the Quantum Foundations literature is in terms of the decision, the freely chosen decision, can only be correlated to the future. there cannot be any correlations to the past or to the space-like separated places. What the non-Nation version of free choice means, it's a weaker assumption that is also called, if you know quantum foundations, you might know it as full support. It's full support. It means that there exists a world in which every choice is taken. I make that choice to drink coffee in our world. There is a world somewhere where I drink tea. That is my weakened version of free choice. I could have made a different decision, but it's compatibilistic in the sense that I could have made that different decision, but I could have been predicted. So I drink coffee. Everybody knew I would drink coffee. I could have drunk tea instead, and it would have been predicted that I would have drunk tea, right? So this is the idea. I weaken free choice. Many people have worked in a binary fashion. Either I'm free or I'm not, right? So if we don't have this free choice in the Nation way, it's super deterministic. But what we argue is no, there is room in the middle for something that is neither super deterministic. We still have retained some free choice and are responsible for our decisions, but it's also not to the point that our decisions are totally unpredictable, right? Did that make sense? It's really the math that I'm interested in. Mm-hmm.
Either you can predict or you cannot, even if you say partially predicting.
Let me explain. Yeah.
How you partially predict what I do.
So,
also predict probabilities of what I will do.
So let me explain that, because that's what Jean-Pierre Dupuy already 20 years ago was arguing. We need to distinguish between two models for prediction. There is what he called ad hoc prediction. Ad hoc prediction means in my world, in the actual world, the prediction is correct. But in parallel world, it might have been incorrect. So it's just in this world here, the prediction is correct. Perfect prediction means that the prediction is correct in all worlds, in the sense that there is this counterfactual dependence between the decision and the prediction. So there are several ways of defining prediction, right? And it's very important to model that. In game theory, this is known as necessary rationality in terms of model logic, right? There's a quantifier on all possible worlds versus only assuming it in our worlds, right? Does it make sense?
Yes, but I need to think about it.
Okay, yeah, we can continue the conversation after that. Yeah, I'm very happy to have debates, and yeah, every debate strengthens the argument, so I always welcome this. Yeah.
So unfortunately, these were, or not unfortunately, they were very interesting answers, but we are out of time, so I cannot take the promised third question. So what leaves me to give you a little token of our appreciation.
Oh,
yes,
wow.
we don't have two boxes. We only have one cup.
Oh, that's very, I'm a one boxer. I pick one box, so that's actually perfect.
And it's not a choice. But thank you very much for the very interesting talk.
Thank you very much, Manuel.
And you have a nice rest of VIScon. Don't forget to review the talks if you want. It helps us. It also may help Ghislain. And yes, go to your next talks. Have fun.
Thank you.